Hello everyone, welcome to the Learning Express YouTube channel. In the series of common source amplifier, previously I discussed about the resistive load and diode connected load. In this video, we will discuss about the current source load. Basically the point is, initially I replaced the RD or simple resistor with diode connected load, and now I replaced that load using current source load. So what is the need of that current source load? Now, few questions are coming into the mind. Why current source load, and exactly what is the current source load, and how this current source is implemented, and how this current source is different from the ideal current source. So these are few questions I'll discuss one by one. So the first thing is, why current source load? So it means, what is the need of that current source load, and what is the problem with resistive load and diode connected load? So basically, in diode connected load and in resistive load, if we want a large gain, so in current source load, if I want large gain, means in general, this AB, yeah, this AB is equal to minus GM RD for single stage transistor. If I want to more gain or larger gain, then I need to increase this RD. But we cannot increase this RD value because of limitation in voltage swing, output voltage swing. So the point is that how to increase this gain. So for increasing gain, if I am using, suppose this is the common source stage, and instead of RD, if I am using here the current source, ideal current source, instead of this current source that I am designing using a MOSFET, if we are using this current source, suppose I, and we are taking output from here, and if we are taking output from here, then the gain will be what? In AC analysis, this will be open. And if it is open, means it will offer the infinite impedance. So the gain will be nothing but V out by V in equal to, V out by V in is equal to minus GM R naught parallel with R of this current source. And this current source impedance is almost infinite because it is open now. So it will be around minus GM R naught. So this is very large gain actually. So intrinsic gain is large gain because this R naught is very, very greater than RD. So this is a large gain that we are getting from here. This is with the ideal current source. And if we are implementing this current source using MOSFET, then what will be the advantages or what will be the problem? I'll discuss in next slides. Okay. So yeah, the first point is a voltage gain. That in usually in the first stage or the single stage, we get this the minus GMRD. And if you want to increase the, to obtain a large voltage gain in single stage, increase the load impedance of common source stage. So if you are using only the single stage, then we need to increase this impedance. But what are the advantages or what are the disadvantages of the RD, increasing in the RD? So I have mentioned here the resistive load or the diode connected load. If we need to increase the load resistance, a large DC drop across the load will peak there. Means if there is a DC load, means if this is your RD, and I am thinking to increase again, then gain can be increased only when this RD is increasing. And if RD is increasing, it means the drop across this RD will increase. If drop across this is increasing, means output voltage is limiting. And if output voltage swing is limited, then there will be other disadvantage of that. We need to get a good output voltage swing. So this is the disadvantage of increasing RD. Now, when we cannot replace the RD with its large value, we need to replace the RD completely with the MOSFET. So what is the problem with here? If we have RD only or the resistor of diode connected device, then with the increasing value, we are getting more drop across it. It means it is following Ohm's law here. This device RD or diode connected device or diode connected device is following simply, if it is a diode connected device, it will offer 1 upon GM or maybe some other value. So if this is a resistor of value RD or 1 upon GM, the voltage across it will increase if we are increasing its value because it is owing directly your Ohm's law. So instead of this, if we are using some load which do not follow Ohm's law, then we can get some good voltage gain without affecting the output voltage swing. So the more practical approach is to replace the load with a device that does not obey the Ohm's law. So the meaning of this line here is that we will not get voltage drop across this device if it is not following the Ohm's law. So that thing can be done with the current source. Because the current source, instead of this RD, do not follow the Ohm's law. Instead of this RD, if we are using the current source, it do not follow the Ohm's law. And if it does not follow the Ohm's law, then the problem is solved. So, so if does not follow the Ohm's law, I mentioned here in the previous slide, if this current source is implemented by some MOSFET, here is some bias voltage, and here a VDD, and this is your input device. This is your output, input. So if it does not follow the Ohm's law, then this particular device is your current source. And it will offer a large impedance. It will offer a large impedance. It will offer large impedance in the range of R0 to infinite. If we are using MOSFET, this is M2, which is also in saturation. Or if it is ideal current source, then it will offer the infinite impedance. So overall, in this case, the gain is minus GM of primary transistor parallel with this R01 and R02 if I'm using M2 in saturation as a current source. Okay. So now point is what is the current source actually? So any MOSFET which is using in saturation, which we are using in saturation, suppose this is your VDD voltage and this gate is biased with some voltage. Suppose the source is grounded or source is connected to some value. So when this biasing is set such that this particular device is acting in saturation, then it is nothing but a current source. Because if this device is acting in saturation, if I'm, for simplicity, if I'm ignoring the CLM, if lambda is 0, means after this particular value of input, and in this region, the current is constant. So it is acting as a current source. So if this characteristic is ideal, means there is a no slope. If there is a no slope, this device will offer infinite impedance. Ideally, this characteristic is existing, but practically this is like this. So this particular slope in saturation region is nothing but 1 upon R0 2 if I'm using second transistor. So this is your input voltage and this is ID. So for the characteristic between ID and V in, this is the input voltage here. It is going to offer like this 1 upon R0 2. So this is the practical characteristics. And if we are reducing this CLM, this R0 2 will increase or this characteristic will approach more toward the practical value or more toward the ideal value, sorry. So yeah, if this is like this, means the lambda is here more and lambda is slightly less and here the lambda is almost 0. So if we want more resistance for getting more gain, we need to reduce this lambda value. And for reducing the lambda value, there are some design parameters, width and lengths are responsible for that. So I am not going into the depth of this discussion, but the point is here that if we have a device which is acting in saturation, it will act as a constant current source, and this current source will offer a large impedance, and this large impedance can be used to get the gain, good amount of gain. Because ultimately, if this device is acting as a load, if this device is acting as a load, then our target is to get the high impedance at this at the place of this RD. So if this is the reason where we are getting high load, so yeah, if this is a current source, then it will offer the high load, high impedance value, and this high impedance will give you the good amount of gain. So due to this, we'll get a good amount of gain. R naught 1 parallel with R naught 2. So if this R naught 1 and R naught 2 are almost equal, then we have very large gain. This is about 2 minus GM R naught 1 or minus GM R naught 2, because R naught 1 and R naught 2 are almost similar but large value. So this value is very greater than this. So we have achieved one target. That's the GMRD is very, very less than GMR naught. So I can say this gain is good gain. So this is the need of current source. So I have taken the diagram here. This is our main input device. Output versus input are taken here. And this particular thing is acting as a constant current source. So here I have taken the PMOS device. So for this PMOS device, if I want to see its impedance, then this is a bias voltage. This is also 0. And this is your VDD. This is also 0 for a small signal model. And if I am looking from this side, the impedance offered will be R naught. The impedance offered from this side will be R naught 2. So we can also calculate by using the small signal here. So if I am using the small signal here, I need to tell all the points here. So yeah, so just make this source to ground, and this is your VSG. Okay, this is a dependent source. Drain. This is your R naught 2. Yeah, this drain. At this drain, I'm connecting a test source. This test source is Vx, and here Ix is the current across the test source. So I am doing the small signal analysis. I can also tell you this thing intuitively. So now apply the KVL here, or KVL or KCL, whatever. So the first thing is this is your grounded. This gate is also grounded. It is also grounded. So first of all, we can say there VSG is 0, because S is also grounded, means source is grounded, gate is grounded. So VSG2 is 0. If VSG2 is 0, this current source will be opened, and overall we can see that this R naught 2 is the impedance that is desired value we are looking for. So this is actually R naught 2 value. I directly mentioned it. So please remember this. If there is, and I think this thing I discussed in previous videos also, if we are looking from the side of drain, your source and gate are grounded, then impedance offered by that device will be R naught. And if we are looking from the side of source and drain and gate are grounded, then it will offer the impedance of 1 upon GM. So this is a simple point. Okay. So in that case, the gain V out by V in will be nothing but minus GM1 R naught 1 parallel to R naught 2. So basically, this diagram I had taken here just to tell you about the small signal analysis. And this thing I also mentioned before. So please look other videos. Now, so how it is different from ideal current source load? So I mentioned the one thing before, the ideal current source, the ideal current source, it offer infinite impedance. It offer infinite impedance while we do the AC analysis, but this current source, practical current source, it generally offer R naught impedance when we are using. So this thing I explained depends on the characteristics. So I think no need to explain it again. If we are implementing the ideal current source or whatever the practical current source using MOSFET, so this is the ideal characteristics. where the impedance offered by is infinite. And if it is a more practical, then this is like this. So this is your R naught inverse. Yeah, this is your R naught inverse. The current source that we are designing using your MOSFET, it is offered, it is offering the impedance R naught. A general, I can say ideal current source offers an infinite impedance. So this is the difference. So now I mentioned here one key point. Output impedance and the minimum required VDS of M2 are less strongly coupled than the value of voltage drop of the resistor. So yes, this point I mentioned here because when we were discussing about the resistive load or the diode connected load, here was a device called resistor here. And this resistor, the voltage across are strongly coupled. The value of a resistor and the voltage across it are coupled. Like this, if I am thinking like this, VRD is equal to ID RD. So if we want more gain, V out by V in, which is what? Minus GMRD. So if you want more gain, we need to increase this RD. If we want to increase this RD, this voltage across the RD will also increase. So if RD is increasing, VRD will also increase. And if this VRD is increasing, means V out equal to VDD minus VRD. So if this VRD is increasing, this V out will decrease because VDD is constant. So this V out will decrease. So it is limiting the limiting the output voltage, limiting the output voltage swing. So this is the problem. That's why I mentioned this point. There was a strong coupling between RD and voltage drop across that resistor. But in case of diode connected device, because this is the current source. Oh, sorry, not the diode connected device. It's a current source. So there is a no voltage dependence on its value. So its impedance is independent of the voltage across it. Because after all, we can see here, this impedance is nothing but slope. So whether we are applying whatever the voltage we are applying, it will offer a impedance that is a constant. Or the voltage drop across it will not matter your output voltage. So there is a no effect of this particular thing on your output swing. So output voltage swing. So output voltage swing is not affected. So there is a no problem in this. Now, if I talk about the design point of view, so I have mentioned with this particular design, we have improved, maintain voltage swing. So that this thing I already mentioned here, because what is the voltage swing? If this is a second transistor which is acting as a load or current source load, this is a bias voltage VDD. Okay, so this is the minimum potential. So if I talk about this VDS to minimum, it is what? It is what? VGS2 minus VTH2. So this potential is a overdrive. So if this potential is, because this potential was previously like drop across the resistor, but here this potential is very small value. So by controlling this gate potential of this device, we can control this overdrive voltage. And by controlling this overdrive voltage, we can reduce less than 100 millivolts by simply increasing the width of M2. So if we are increasing the width of M2, we can reduce the overdrive. And if we can reduce the overdrive, then we can improve the swing. So this is the point here. But in case of RD, it was like increase the value of RD for increasing the gain. We were about to limiting the voltage swing. Now we also improved with voltage gain. With this design, we also improved with voltage gain. So how we improved the voltage gain? So because R naught 2, which is responsible for gain, can be improved by the length and width of the M2. If you are increasing the length, if you are increasing the width, then we can see with the relation lambda is proportional to 1 upon L. So if we are increasing the length, we can reduce the lambda. And if we are reducing the lambda, our R naught can be enhanced. If R naught is enhancing, our gain is also enhanced. So with this, we can conclude longer transistor yield higher gain. But for that, the penalty is larger capacitance will come into the picture. This thing I already discussed. If you are increasing the length and width, then capacitance is okay. The capacitance is COX, some K times of COX WL means area is multiplied. So if you are increasing the length or width, if area is increased, then capacitance will be increased. And if capacitance is increased, then there are some other issues will come into the picture. Output voltage or can say swing will again disturb. So this penalty is also a limitation, and this is other limitation that I mentioned separately. So this limitation is voltage swing limitation due to sizing. So if you're increasing the sizing, just look at this point, this overdrive voltage will be limited because overdrive voltage is inversely proportional root of W by L of 1, first transistor. So the overdrive voltage of first transistor will be limited if L1 is scaled, but W1 is not scaled. So if you're increasing the L1, but W1 is not scaled, the overdrive voltage increasing, and this thing will limit your output voltage swing. Because if VGS 1 minus VTH 1 is limited, means drain to source voltage, because this value is a minimum drain to source value. This is your minimum. This is your minimum value. So if this value is limited by the sizing of transistor first, your swing will be limited, or the minimum output voltage value will be dependent on the scaling factors of this WL. So this will be limited here. Yeah, second limitation I have here, the gain is also limited due to the sizing. Because GM1 is proportional to under root WL first. Scaling up only the L1 lowers the GM also. If by keeping the W1 constant, because W1 is constant, we are keeping the W1 constant to uh, limit the capacitance value. If we are increasing the L1, we are scaling the L1, then GM1 will reduce. And if GM is reducing, then the ultimately our aim of achieving high gain is not accomplished, because ultimately the gain is dependent on GM, and GM should be high as max as possible so that we can get good gain. But here with the scaling, we are getting lower gain value. So your lower GM value, so it will reduce the gain also. It will limit the gain also. So these are some few points about the sizing of the device, where we are affecting our gain, where we are affecting our swings. So we cannot increase the sizing or we cannot decrease the sizing as without any kind of good calculation. So here I mentioned the key point. If these issues are unimportant, then intrinsic gain is defined like this. GM and R naught are defined like this in terms of sizing. Yeah, if these issues are unimportant, then we need not to change the W1. If W1 is not changed, then ID will increase with if yeah, ID will increase in overdrive. If W1 is not considered to be changed, means ID1 will increase with overdrive and intrinsic gain will decrease. If L2 is increasing, L2 increment keeping W2 constant will improve gain again on the cost of higher overdrive voltage. So if we are increasing the L2 by keeping the W2 constant, we can again improve the gain. But there is the problem of overdrive limitation of second transistor. Because ultimately we need to keep the second transistor in saturation. And if this overdrive is limited, the higher overdrive voltage of this transistor M2, we are limiting yeah, we are again limiting the swings of the transistor. So technically, first analyze this point, and by varying this L1 and L2, you can see that how this swing and um, overdrive voltage is affecting the transistor's operation. So this is the example I have designed related to this. I'll discuss in next video. So from the theoretical point of view, I have mentioned these points in this. So first of all, why the current source load? I mentioned few points here. Yeah, these points are there. And after that, what is the current source load? I tried to explain the current source load. And later on, how it is different from ideal current source and the practical current source. So this thing I explained here. Yeah, I mentioned the key point here. And later on, I talked about the design point of view. This is important. And it's also technically in-depth discussion. So if you're not getting clear with these things, you can ask me later on. So these the limitations are also discussed basis on the design perspective. So this the gain limitation, and before it was the voltage swing limitation, depend on the sizing. So I think this is enough for theoretical discussion of this particular type of topology of common source transistor or common source amplifier. In coming video, I'll discuss this example, and later on, I'll discuss about the common source amplifier with active loads. So I think this is enough for this video. Thank you.